So what we have got? We have got this logistic regression, these values. Let us compare these values with what we have obtained. Minus 13, 2.8, 0.09 and 2.39. So this only we have got the same values we have got from the same data set, and whatever has been reported here, you ignore that. Let us go to Excel file, because this program has to be found even though I got it from the net. So we go by step-by-step method. So whatever beta values so we got, that has been written here. Beta 0, beta 1, beta 2, beta 3. 3 variables were there, and this is the intercept. As I told, this lambda is nothing but 1 by 1 plus e power minus z, where z is equal to beta 0 plus beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3. So that we are doing. So these are nothing but the means of the given x variables. The means of mean of this first variable, second variable, and third variable. So these are nothing but the means of the given x variables. Then beta 1, beta 2, beta 3. You can see this. Of course, this intercept will always have the value x0 as the variable, which will always take value 1. So I am not writing that separately. So now, because z is nothing but what? Beta 0 plus beta 1 into x1 plus beta 2 into x2 plus beta 3 into x3. I am multiplying these three things, adding that, and also adding the intercept, because beta 0 has to be added, right? Beta 0 plus beta 1 into x1 plus beta 2 into x2. So that z value you have got. Once you got the z value, this expression you see 1 by 1 plus e power minus z. So I am taking e power minus z. Then the denominator term is 1 plus e power minus z. Then we are getting this lambda value, capital lambda value, 1 by 1 plus e power minus z. So once this has been done, the formula is what? Lambda into 1 minus lambda. So lambda into 1 minus lambda is this. So once you have got this single value, then the betas are what? These quotients of x1, x2, x3. So that along with that, we have to multiply this lambda into 1 minus lambda. So then you will be getting these values. So now we can match these values, 0.533, this one and that one. Let us see the 0.533, 0.018, 0.449 rather. 0.449, and that is matching with what values we have got. So this is the way of finding the marginal effects. Now you will be asking what is the difference between, because in case of the usual regression, the regression quotient of y on x is defined as average change in y per unit change in x. But in case of logistic regression, we will be telling not the directly the quotient, but e power that quotient. But this is not e power, this is something else, right? It is not just e power, it is the whole expression. So marginal effect is different from the usual way of interpreting. So this gives nothing but the slopes of this model. Now let us come back to the R program. So who are asking about marginal effect? Any response? Yesterday one madam was telling, right? Who was she who told that marginal effect? Wall test we will be telling, right? Now here itself, let us see the results. For that, let us take a different program. So we will see this data set in two different ways. One way is, so this data, let us discuss what it's all about. This data pertains to presence of heart disease in human beings in different age groups. So you can see age group 25, then 30, 35. Presence means 1, absence means 0. That has been denoted like that. So as the age increases, the occurrence of heart disease seem to be more. You see, in 50 age group, in 55 age group, 60 age group and all, more of ones we can see. So now, yesterday we were asking about proportion data. Instead of ones and zeros, whether proportions can be used. There's less than 1 can be used. Proportions which are lesser again can be used as y values. So yes, they can be used as y values, and they are not called proportions. They are again ones and zeros, but we call them as aggregate binary. So the same data will aggregate and use. So ones and zeros are there as presence and absence for the main variable. Now for this data, let us run the logistic. So what is this data? Presence of heart disease as a function of age. Y is equal to a plus bx. Instead of a plus bx, we are doing y is equal to 1 by 1 plus e power minus a plus minus of a plus bx. So the corresponding R code I am opening. Now let us read that coronary heart disease data. And the data has come inside. There are no missing values. The summary of data we are getting like this. So you see, Y has to be told to the R software that it is categorical rather than continuous. Otherwise, like this and all values it will start coming. So what we do, we change it into categorical. Factor of this means we are changing it to categorical. So now you can see, out of 100 observations, 57 persons do not have any heart problem, but 43 persons have heart problem. And age, you can see, it is that we are taking as a continuous variable. Now let us see this. So instead of seeing it zeros and ones in an individual fraction, we are going to do aggregate binary. We are seeing aggregate binary. Age wise we have there, and you can see in this age group 25, of the 10 observations, 9 do not have heart disease. So 0 and 1 is having heart disease in this way. You see in 55, you see of the 17 people, 4 do not have, but 13 have some problem of heart disease. So like that. So the difference between that just binary and what you ask the proportion is, this is proportion means we have to deal with aggregate binary. Aggregate in the sense that even though the data are noted down as zeros and ones, we will take the proportion, something like if we are going to fit the probability of occurrence of the heart disease, probability of Y is equal to 1, then we will be taking the value 1 divided by 1 plus 9. That is 1 divided by 10. Then 2 divided by 13 plus 2. 2 divided by 15 like that. So that they call as proportions or aggregate binary. So even though they are zeros and ones only. Now moving ahead, we are using this logistic regression, and this is binary data, so family binomial. We are fitting coronary heart disease on age for this data set DF2. Once fitted, you will be getting these two values. So you can note down these values for minus 5.1 and 0.11. Why I want you to note down? Because this has been run upon just binary data, not aggregate binary. It is just binary data. So the same data set, after doing aggregate binary, that is the proportion data, we'll get the same results. Let us see that. So people were asking about Wald test. Wald test is nothing but this Z test. Even though in many books Wald test they tell that that Wald statistics follows chi-square distribution. Now one thing is that these Z individual Z values, they are nothing but standard normal variates. What are they? This minus 4 point. That is what? That is nothing but estimate divided by standard error. Now, in any testing of hypothesis problem, there are three things: hypothesis, test statistic, decision criteria. What is the hypothesis here? The individual regression quotient is 0. Beta 0 is equal to 0. So now instead of t, we are going using put z, because in regression analysis also, usual multiple linear regression analysis also, we will be discussing the same thing. Test for individual regression quotient is done by t test. But there and here the difference is that there we will have the residual variance estimator. But here always we will take the variance as 1 only, that whatever deviation. So here we are using z. And this again can be told as the Z score can be told as the Wald test, because standard normal variate, the square of any standard normal variate with 1 degree of freedom is a chi-square variate with 1 degree of freedom. Square of any standard normal variate is a chi-square variate with 1 degrees of freedom. So both are one and the same. Wald test, many books they would have written, it follows chi-square test, but square of it is the same, this Z value. So from this probability value, exact probability value itself, we can see whether these are significant. Yes, Wald test tells that they are highly significant. You can see e power minus 0.6 means 2.5 divided by 1 followed by that many zeros. That is, it is almost 0. That means it's very highly significant. So it is less than 0.01, less than 0.05. So it is highly significant. So another thing which you can note down, this null deviance and residual deviance. Null deviance means what? If no explanatory variables are included in the model, what is the deviance? But if the explanatory variables, here it is age, it is included, the deviance should decrease. So that is a sign that yes, there is an effect of age on the main variable. So always from null deviance to the next one, it should decrease once you have included that explanatory variable in the model. So now one more thing you note down, 1, 1, 2. Why I am asking you to note down these values? I have asked you to note down 5 things. One is intercept and age, of estimates of intercept and quotients of intercept and age. This quotient of age minus 5 point something 0.11, and the null deviance, residual deviance, and AIC value. AIC is Akaike information criterion that tells about the goodness of the fit of the model when comparing two models. In case of multiple linear regression, R square, coefficient of multiple determination, you will see for maximum R square. But in case of these nonlinear models or time series models, you will see AIC, you will go for minimum. That is when while comparing two models. Individually, absolute value, there is no meaning. But if you want to compare two models, you will go for that model for which AIC is the least. So once you have noted it down, let us, so the same data, this coronary heart disease data, I have brought in a separate file with age 25, 30 to 35, 40 and all. N is the number of observations within each age group, and R is the occurrence, that is within this age group, Y has occurred once. That is once, there are 2 ones, there are 3 ones, 5 ones, 6 times ones out of 13, 5 times. So people were asking about whether proportions can be used in this logistic model, and these are the proportions R by N. This is the proportion 0.1 and all. But you should keep in mind that even though they look like proportions, we are dealing with Y values, that is the main response variable, as 0, 1 only, 0 or 1 only. In this way it goes. So got the point? Now let us close this. We will analyze this data. So let me take this portion. So now let us complete this earlier exercise. First, let me complete this. Aggregate data we are discussing. In order that we don't get confused, we will write it separately. So this aggregate data, which I have told the table that coronary heart disease versus age, that I am going to read. So this may aggregate binary. So let us see what. So the same data set has been brought here. Age N, and within N how many ones are there, and R by N. So this is a proportion data. And for this we are so R by N is there, you see, R by N is there, and what more is there in the syntax? Age is already there, data is this df1, and you see weights. This is a particular thing which is changed, which is different from the earlier one. So earlier one also, here it is there, you see that weight is equal to is not there, because they are individual ones and zeros. Only change which has been done is this syntax has been added. That is, out of how many observations this ones have occurred, like that. So group wise data. So this weight is equal to N. N is the out of how many observations, right? So this has to be added, and let us see the summary. So you can see the summary M3 only we are seeing. The estimates you will get exactly the same estimates, because even if you run it as ones and zeros or aggregate binary, that proportion data you call, but the estimates will be same. But what here is there, the null deviance and this residual deviance, they are different. Earlier we had a 3-digit number, right? Some 100 or something we got for the same data. You see 136 and 108. Here it is 28 and this. And AAC value also has changed. So it depends upon how you are arranging the data. So, and you can see that reduction in the deviance. Here also it is around 28. And here also it is around 28. AAC value, of course, it has changed. So accordingly, while comparing model also, you have to see how the data has been arranged. Now, let us move on to prediction. So once you have fitted the model, what is the use of it? This model has been fitted, and what we do, we will read the same data because we want to let us predict for the same observations. We'll read the same data and put it as X. Then predict the responses for using which model, the fitted model we have to give, and for what observations we are predicting, these X observations we are predicting, what we are predicting, the response we are predicting. So let us see. So the predictions we have got as how many observations were there? 100 observations were there. And for each of the thing we have got prediction. How it is fitting. It is taking the quotients in the logistic regression model -5 point something and 0.01. Just it is plugging the values of X. X means what? Age. Age value is plugging, and whatever we are getting as Y will be between 0 and 1. Even though we have given the input data as 0 and 1, the output will always be between 0 and 1. It can be likened to a probability, because probability, you know that the limits are between 0 and 1. And you may be asking, many values are same. Many values are same because the X values are also same. This is belonging to age group 25. So only one age group, one number is there, 25. Always the predictions will be same corresponding to that age group. Then 30 age group starts. So till this point they are 30. 38, there also it will be same. You can see as age increases, the probability of occurrence also increases. 0.83, like that. So it is 60 age group, I suppose. So you can have a cutoff from your side. Greater than 0.5, that means more prone for heart disease. Less than 0.5, less prone for heart disease. Like that, we can have conclusions as well from this fitted model. For a new case, so any new person is coming, age just you fit in the age, you will get the corresponding status. And again, that person who is coming, he should belong to the same range, that is same race, same region, all those things. So that the prediction values, holdout set should be, new case should be belonging to the same group. So now, yesterday we were telling the 6 things we will discuss. First thing, indicator variables, already in multiple linear regression we have done with it. Logistic regression for forecasting, one problem I have brought. And green book we have seen that how to fit that logistic regression, and marginal effects also we calculated. So 2 more topics are left. One is multinomial logic, another is probit. First, let us finish off with probit, then we will go for multinomial logic. So we were discussing, I think on the first day, I suppose, on Saturday, I suppose, we were discussing this multinomial logic. Let us see particularly these variables only. What variables I have chosen? I have chosen one variable called SCS, that is socioeconomic status. Another variable called PROG, that is the program a student will take. Either it could be vocation or general or academic. So here you can see the program has 3 levels. Again, another variable is right, which is a continuous variable. Continuous variable, no problem. But what we are going to fit? Program upon right and socioeconomic status. So this program occurs on the left hand side, that is a response variable or the main variable, which has 3 levels. It is not binary, it is more than 3 levels. So the levels are vocation, general and academic. And upon what? Upon right, no issue. Upon SCS, socioeconomic status, low, middle, high. Again, there are 3 levels. So 3 levels means 2 indicator variables will be used for SCS. And we should also keep in mind that we should keep one level as the reference or base level. So in case of this socioeconomic status, low, medium, high, it is a ordinal data. You can order them or grade them. So always we keep low as the reference level, because low is in some way less than middle, and it again middle is in some way less than high. But in case of vocation, general and this academic, we cannot have that gradation. They are just nominal. They are groups. More than that, we cannot tell anything. Something like this vocation can be likened to arts, general can be likened to science, and academic can be likened to, say, engineering or professional course. So then also we cannot tell that this is superior to that or inferior and all. Just there are 3 groups: vocation, general and academic. So now let us come back to so in case the so this model has been written again for the case where the response or y variable is having 3 levels. So 3 levels means there will be 3 equations. But again, this equation has been written for the response variable, which is ordinal. So you can see ordinal 3 equations. The intercepts are different, but the slope is same. But in case of multinomial, that is when it is nominal data. So not only the intercept, the slopes also change depending upon the number of groups. So 3 levels are there, means the slopes also change. So you should keep this difference between these two multinomial logic. One is ordinal, where the slopes are same. You can see I written beta 1, beta 2, and everything same in the equations. But in case of this multinomial, where the response variable, we cannot, the levels we cannot grade or order them. Even the slopes also differ, or the beta quotients also differ, depending upon which group it belongs to. So now this pi is nothing but probability of occurrence of that particular individual in that particular jth group, and this pi is the probability of occurrence of the particular individual in the kth group. Like that we have to see. Again, while writing the equations, we are writing till the k-1 groups only, because any of the last equation with the total probability. We should always keep in mind that the total probability of all these pi's, that is probability of occurrence of that group, will be always be 1. So the last group pi k will be in terms of the other groups, 1 minus of pi 1 minus pi 2 minus etc. pi k minus 1. So n observations will be having, and qualitative response variable with k categories. So that only we have here. So we have 2 equations. Academic has been taken as the reference category. That's why it has been written in the denominator. And general and vocations are the other 2 categories. And you can see intercepts are different, slopes are also different. Now let us come back to the program. So let me load certain packages. Seems these have already been installed. Now let us read that particular data set, that table school. So it is something like there are many students who are opting for academic or occasional or the third one, general streams, based on their right scores, that is exam scores and the socio-economic status. So you can see socio-economic status, who are high, so having socio-economic status, they tend to go for academic. Other things, almost it is in middle also, you see, they tend to aspire for academic programs. Now, based on right, if you want to take a mean of it, so these are the values. You see mean of for academic score students. So they tend to be more than for that right variable. And for this general, this is this, and standard deviation also has been given. And socioeconomic status, let us see. As per socioeconomic status, what is that? So as per socioeconomic status, this is the thing. This is as per program. This is as per socioeconomic status. Now, we have taken academic as the reference level. So that has been written here. In the same way, the other one also. Let us see this, whether will this works or not. So now this should be taken as factor. So they have been taken as factors. So we have assigned academic and low as reference level for this program and SES. Now we are running the multinomial logistic regression with program as a function of socioeconomic status and right for this particular data. So we have got the coefficients as these intercept, even the slopes are changing, and because SES is at 3 levels, 2 indicator variables have been used with low as a reference category. So for the indicator variable high, these are the questions. For the indicator variable wherein always it will take one when middle SES are there. This is the thing. Right is a continuous variable, only one. Standard errors are given, residual deviance and AIC. Now, for these quotients, we can go for that particular Z test or wall test. So we can see whether so the P values and the Z values we can write down. So Z values are given here and corresponding P values. If the corresponding P values they are less than 0.05, we can tell that these corresponding variables are significant, that quotients are significant. So now, as we discussed sometime, what matters in logistic regression is not the direct quotients, it should be exponential power this. So exponential power that we have taken. So directly we will not be seeing the quotients. We will be seeing rather the exponential power. So now you can see from the model fitted, let us see which student is having more probability of opting for which program. So as I told, the total probability is always 1. You can see it, you can total it 0.14 plus 0.33 plus 0.51. The total probability is always 1. And you see the first student appears to go for vocational program. The second student, same vocational. So in this way it goes. So what else is there? So the third student has a more probability for going for academic program. So like that we can predict from the fitted model. So now with this thing, the last topic, let us take Probit model. First, let us see what the data is all about. The data is given here for this concentration. If you are giving to this many insects, like this many insects die, the proportions are given. So for this data, this concentration could be some dose of insecticide, fungicide and all. 50 could be the number of insects and how many insects have died. So this is the dose response data. This is the dose, these are the responses. So that's why R is written. Now let us take this code and bring inside. So let us read this data, dose data. We read that. And these are the data concentration, the group wise, and what are the responses and the proportion. So we run in this. Then afterwards, let us concentrate on only Probit. So you can see GLM, the usual generalized linear model. And what we are doing, we are having not only how many are alive, that is out of this 50, 44 response means 44 that died, we say the insects have died because of that insecticide. So 50 minus 44, that is alive, that is how many are alive. That also we are giving either this way or that way. Either you, because the total is same, n, and we are giving the link function as Probit. So let us run this. So we are getting the quotients for the Probit model as minus 0.37 and concentration 0.17. And what is the difference between Logit model and Probit model? For most of the cases, they are same. If for the same data, because age and coronary heart disease also we had the same table, right? Number of persons and within that how many are affected. But the difference lies in case of say more of disproportional data, like if the number of observations of zeros and ones are too much separated, like out of 100 there in that coronary heart disease we got 57 and 43, right? So there both Probit and Logit will give the same results, but instead of that it is 80-20 or 20-80 like that and all. Extremes are there, there will be different result. One more thing I read in that green book is if that logistic Probit model is there, the quotients are there, you are just multiply by 1.8, 1.6, each of the quotients you will get what the quotients of Logit model. And fairly it works. I also noticed that. Now, what is the use of this Probit model? So for the use is this one. We will be looking for effective dose 50, lethal dose 50 from this proper by this thing, or rather we will tell median lethal dose. Now we will not tell mean, median lethal dose. So if the logic, if the Probit model is like the constant plus quotient into X, that only we got there, right? So in that case, the LD50 will calculate as minus constant divided by quotient. Just you can calculate directly. But in case you want to get fit for say LD90 or LD75, the formula is this: Probit inverse normal P minus constant divided by quotient. For logit, it is very easy. Log P by 1 minus P. P is the probability that it is 1. So like that, this Probit model can be used. So now there are certain things in the chat. So it is in the chat box, it is written how the negative value of interceptor to intercepted is interpreted, and if the intercept is significant, then what it indicates. This I can mail to the organizers because offhand I am not able to tell this. So we will stop here. Any further questions? So this I have noted down. I will just read and I will mail to organizers. They will in turn respond to you. Anything else people want to ask? Again, these things are over. Question and answer is over. Now, anything else? So these were the questions, right? Marginal effects, this all test, then this proportional data, how to handle. Okay, Dr. Suresh K has told, thank you, sir. So that means the lecture is over. So now, okay, this particular question I will respond to the organizers. Thank you. I'll leave.
Good morning.
I know it is very difficult for you because you have your IRC starting.
Yes, ma'am.
So it is in the afternoon, I hope?
Yes. Pre-IRC, that is in the afternoon from 2 o'clock and IRC from 18th. So today also we need to be present. That's what we have been asked.
Okay.
Yeah. So, and thank you for preponing my lecture because
yes.
I did not want to leave that. I wanted to discuss this. Yeah.
Very good. So that's nice. I will just take 2-3 minutes to briefly introduce Dr. Ranjit Kumar Paul to the participants of this training. So Dr. Ranjit Kumar Paul is a senior scientist in our sister institute, that is Indian Agriculture Statistics Research Institute. He has foreign exposure of South Dakota State University, USA, because he visited there and worked there as a visiting scientist. He is an elected fellow of NAS and recipients of many Young Scientist Award, one from NAS in Social Scientist group, another from ISAS, Indian Society of Agriculture Statistics, and one from Society for Application of Statistics in Agriculture and Allied Sciences, SASA, and also received ICR Lal Bahadur Shastri Outstanding and Young Scientist Award for Social Sciences. He has been teaching also, and he has guided so far 4 MSc students in agriculture statistics. And of course, he has been advisor of many students, very favorite teacher for the students in advisory committee. So almost all of my students have him as an advisory committee members and many other students also. So, and he is presently also guiding 2 PhD students in agriculture statistics. He has published more than 150 research papers in national as well as international journals, very reputed journals. So besides that, like he has been constantly working with NIAP in prestigious projects of NIAP. Like one is that market intelligence project. He has been associated with that. Then he's also associated with another project, value chain also, like he is working on. So constantly he has been working with the one or the other projects of NIAP, which are in network mode. So I would like to invite Dr. Ranjit Kumar Paul for his actual lecture, in which he also has practical experience of doing real-time projects. So Dr. Ranjit Kumar Paul, like now the floor is yours.
Thank you, ma'am. Thank you for giving me this opportunity, and thank you for your nice words. Very good morning to all the participants, all of you. We'll start directly. We'll be discussing about the time series model, time series analysis, of course, giving much more emphasis on the practical part. I hope the introduction of R software package has already been done, and you are well versed with this R software package. So of course, during our analysis, whenever we'll be doing the practical part for the time series analysis, we'll be introducing each of the function and the packages which we'll be using for analyzing our time series data, and that time also you can have your comfortability. So we have around 2 hours or so, and we'll be discussing time series as well as panel data regression, and giving much more emphasis on the practical part. So just sharing the slides, I have a brief presentation just to introduce the topic, just to say the background of the model, what are the steps of building the model and how it can be built up very easily, and then going for the practical part by using R software package to analyze all the practical data. I hope this is visible. This presentation is visible.
Yes, your presentation is visible as well as moving also.
Okay, thank you, ma'am. So, so today's discussion is time series model. You know, statistical modeling, you know, mathematical model, and I am sure the regression model has already been discussed with you, because that is the prerequisite for having a knowledge of time series. because regression, I think it is the most important and widely used technique across the discipline we belong to. You need not to be a statistician or econometrician to apply your regression model. Any discipline we belong to, in our day-to-day research activity, we use the regression analysis, and that's most favorable and most widely used technique. So assuming that we have knowledge of the regression model, and we'll be moving towards the time series model. Before we go for the time series model, I'll just give you one differentiation or one difference between regression and time series. In a regression model, you know, whenever we actually talk of any statistical model, as long as it belongs to the parametric domain, every statistical model is based on some crucial assumptions. Until and unless those assumptions are fulfilled, we cannot go ahead. Though with the help of computer and help of statistical software, we can apply any model to any data set. But at the end of the day, we may be misled if the assumptions for the model are not satisfied by your data under consideration. So whenever we try to apply even a simple model to a data under consideration, we need to verify, we need to ensure that the data satisfies all the assumptions for the model to be applied on your data. For example, in a regression setup, you know, our dependent variable or response variable that has to follow a normal distribution. But hardly whenever we actually analyze our data set in practical sense or in reality, we hardly check whether our response variable is following normality or not. But it is to be checked. Similarly, if we have more than one regressor variable in your data set, in your model, then those regressor variables should be uncorrelated among themselves. Then you have the assumptions on the error term, that error term which is appearing in the model, that should follow some identically independently normally distributed with a zero mean and a constant variance sigma square. So these are the basic assumptions in a almost any model, but particularly in the regression model. Assuming that you all know these things, and the main difference between the time series and the regression model is that regression data is that in a regression setup, the observations are independent. The response variable, for example, y, we have a response variable. Okay, we collect the observations of the response variable as well as we collect the observations on the other regressor variables, and the observations on the response variables are independent in a regression setup. That's why if you just shuffle the data set, for example, first row in a y, if you take it to the last row and last row in first row interchange, then also you do not have any difference on the parameter estimate in case of the regression model. But in time series, the observations are not independent, they are rather dependent. So this is the basic difference between your regression data and the time series data. Regression data, the observations in the response variables are independent, whereas in case of the time series data, the observations on the dependent variable or response variable, they are dependent, and the ordering of the observations is having important meaning in time series, whereas the ordering observations has no meaning in case of the regression. Okay, so this dependency structure in the observations of the response variable, we try to incorporate, we try to accommodate in terms of building a model, and that's the time series model. So the basic time series model, obviously time series model may be simple as well as complex. There are basic two broad categories. One is a linear time series model, another is non-linear time series model. So we'll be concentrating on the linear model first. Linear time series model, I hope all of us have listened, have heard the name of linear time series model like ARIMA, because I think at least once we have used it, we all have used with a particular data set. So linear time series model, namely ARIMA, that is autoregressive integrated moving average model, or sometimes it is known as Box-Jenkins model, because the model was proposed by Box et al. In 70s. And this model has been very widely used in the literature for forecasting or prediction of the time series data set, including say yield of the crop or price of a particular commodity or anything, any data which is being collected over the time frame. Now, in a time series data, so the time component has an important meaning. The ordering of the observation has an important meaning. Now, how do we actually collect the time series data? the basic idea of time series data is that the frequency of the observations or the interval must be equal for the whole length of the data set. For example, if we just collect the data, say price data, monthly data, then every month in a year, we must have a data set. We must have an observations. Similarly, if you are collecting the yearly data, for example, say yearly rainfall or annual rainfall in India over the last 20 or 30 years. So for every year, we have an observation. We have an observations. So if we just define the time series, that when we collect the observations on a particular variable on equally spaced time interval, that's most important, equally spaced time interval. If you fix the time interval as yearly, then every year you must have an observations. If you fix time interval as monthly, then every month it is the observations. It may be quarterly, the time interval may be anything. It may be hour, it may be second, minutes, day, week, quarter, month, seasonal, anything. So whatever time interval we fix, that has to be constant throughout the time point or throughout the whole range of the data. Now, in ARIMA model, that is auto-regressive integrated moving average model, this is one of the most widely used linear time series model in literature and in practice also. By the name itself, you can see there are three main parts. One is auto-regressive, second is integrated, third is moving average. So auto-regressive, you can consider it as a separate model. Moving average also, you can consider it as a separate model. And integrated, it comes into picture when the assumptions of stationarity is not valid. So as we have discussed earlier, that any statistical model, whatever we use in general, will have some crucial assumptions that have to be satisfied by your data before you actually apply any model to your data set. Similarly, in the linear time series model like ARIMA, which is also Box-Jenkins model, that is auto-regressive integrated moving average model, it has some crucial assumptions. So first assumption is obviously it's a linear. We are obviously applying this linear model to the data. So the first assumption is pattern is linear. The data pattern over the time point should be linear in nature. Second assumption that's most crucial is the stationarity. Stationarity in layman language, we can think of that the mean and variance of the variable should be constant over time point. Mean and variance and also covariance should be constant over time point. So that's the weak stationarity. We say in general, stationarity means the weak stationarity only. But you can in statistical language, we say that up to second order statistics is constant throughout the time point. Up to second order statistics, that means mean, variance as well as covariance should be constant over the time point. If it happens, then we say that the data is stationary. But in most of the practical situation, you will find that this assumption is violated. You may not have a data set which is having a constant mean over the time point, or it will be having a constant variance over the time point. It may not happen. If it happens, then basically there is no need to forecast because the variability is not there in the data set, and you can observe the pattern existed in the data, and you can actually see that, or you can actually guess that what will happen in the next time point or so. So in most of the data, in most of the practical data set, we find that this assumption of stationarity is violated. And if a particular assumption is violated, we cannot go ahead to apply this particular model to the data until and unless we give some treatment to the data so that the assumption is ensured. So the assumption is valid. So that's stationarity assumptions. And if it is not stationary, we say it is non-stationary data. For a non-stationary data, actually the integrated word comes into picture, and then we go for some kind of differential or so. So this is the stationarity condition, that constant mean, variance and auto covariance or correlation up to second order statistics. Okay, and if the stationary condition is not valid, if it is violated, then we go for some kind of differencing or some kind of transformation. Either you can go for differencing. I think we all know what is differencing. Differencing means that we just take the difference between the present and the immediate past observation. We take the difference between the present observation and the immediate past observation. That is the difference data, first difference data. Okay, we can go for some log transformation also in order to make a non-stationary data to a stationary one. And also there are several statistical tests to check actually that whether my data has become stationary or it is still non-stationary. So all those things we can see in practical part, that how we can go for it. There are statistical tests like Dickey-Fuller test. I'm not going into the details of this. I will share this slide to you. If you are interested, then you can go for this, or it is available in any of the textbook of the time series model, where you can see that how the stationarity test is being applied, what is the form of the test, how the conclusion is being made for testing the hypothesis. There are many tests like ADF test, Dickey-Fuller test, Phillips-Perron test, KPSS test, like this. Many tests are available. So any of the tests you can apply. Of course, there are some difference in the power of the test, but in general, in most of the data, you will find the similar result for all the tests. So any of the tests you apply, in general, by default, we go for ADF test, that is augmented Dickey-Fuller test. We can also go for other tests like Phillips-Perron or KPSS. Now, as we were discussing that ARIMA model, that is autoregressive integrated moving average model, it has basically two separate model. One is called AR model, that is autoregressive model. In bracket 1, it definitely determines or indicates the order of the model. So AR is autoregressive model, and within bracket, the value 1 or 2 or so, this is the order of the model. So if you see the first model, that is AR1 model, which is yt equals to a constant mu plus kind of regression coefficient or AR coefficient phi1 into yt minus 1 plus an error term, that is epsilon t. It has a very similarity with the usual regression model. If you think of a regression model containing a single regressor variable y on x, so we can write down y equals to say alpha 0 plus alpha 1 into x plus epsilon. That is your regression model. And you have a clear similarity with that regression model to AR1 model. So AR1 model, we are writing yt equals to mu plus phi 1 yt minus 1 plus epsilon t. Here the suffix t, obviously it denotes the time point. Yt means that observations at time t. Yt minus 1 means the observations at time t minus 1. So though there is a similarity between a regression model and time series model, but as because the assumptions are different for regression and time series, so we cannot use the estimation technique which is used for regression model. The estimation technique for estimation of the unknown parameters in the model is altogether different from that of the regression model. So here yt, obviously the response variable at time t, yt minus 1, observations on the response variable in immediate past, that is the time t minus 1, and epsilon t, it is the error term. We say in time series concept, we say this is the noise, IID noise, identically independently distributed with zero mean and constant variance sigma square. So the assumptions of the error term will remain same as that of the regression model. Okay. Now, so this is the model yt equals to mu plus phi 1 yt minus 1 plus epsilon t, and the assumptions of the error term you just write down as we write down in the regression case. Now here yt minus 1 is the observations on the response variable on the past epoch. Okay, this is not the, as such this is not the regressor, but we can consider this, or it looks like that it is a regressor in this particular model. So if you just tally this model with the simple regression model, you can very easily understand that in a regression setup you must have at least two variables, right? To write down, to develop a regression model, you must have two variables at least. One is a response variable, another is the regressor variable. Or in other way, we say one is an effect, another is the cause in a regression setup. But in a time series setup, even if you have a single regressor variable, a single response variable, say yield of a crop over the time point, or price of agricultural commodity over the time point, that is the single response variable. Okay, with the help of that single response variable, you will be in a position to develop a model that is a time series model which will help you in predicting the future. So here yt minus 1, it is nothing but the value of the response variable at the past time epoch. And why this is named autoregressive? Because it looks like a regression and the same variable yt is regressed on its own past. In this sense, it is auto. Yt is regressed on yt minus 1. variable is the same one, response variable. So current observation is regressed on its immediate past or its past observation. So in that sense, it is auto regression. Similarly, the moving average model is little complex because it is based on the error term or the past error term. Epsilon t minus 1, epsilon t, these are the basically error term, and the current observations of the response variable is regressed on the past error. So that's the moving average model. And when we combine these two, auto-regressive as well as moving average, we can get ARMA, that is auto-regressive moving average model. Simple combination of these two models. And in a particular model, obviously there should not be two intercepts. So one intercept is coming mu and error term also combining one. So yt equals to mu intercept and intercept. Phi 1 is the regression coefficient or AR coefficient. Theta 1 is the moving average coefficient and epsilon t is the error term. So this is the third equation is the ARMA, that is combination of autoregressive model and the moving average model. And the last one is the ARIMA, where actually the stationarity and non-stationarity comes into picture. That means when a data comes in your hand, we'll actually try to validate the assumptions mean for the data set. And there, if we find that the stationarity assumption is violated, then we go for transformation of the response variable, either in terms of the log transformation, or we can go for differencing the data set to make it to make it stationary. So here y prime, this is a difference data, and if we just regress the difference data on its own past and the past error term, so this will be your ARIMA, that is auto-regressive integrated moving average. Integrated means once you have differentiated the data and then you are combining this, or you are just regressing the difference data on its own past. In that sense, it is integrated. So this is the basic functional form of the ARIMA model and its different part. This is in more detail, that if you have say order more than one, here we have actually concentrated on order one. That means present depends on immediate past. That's it. Present value of the observation of the response variable depends on immediate past. So that's why this is order one. Now it may depends on last two observations, or last 2 lag, or last 3 lags, last 5 lags, like this. So if we just write down in general, it will be like P. So if the present observation depends on last P lag, so it will be ARP model. Similarly, MAP, that means moving average case, if the present value depends on the last Q observations, last Q lag of the error term, then we say that it is moving average model of order Q, like this. Similarly, ARMA also, P and Q in general order, and then ARIMA. Then there are several other things also, like seasonal ARIMA is there. If you are having a monthly data, okay, there may be a seasonality coming into picture, and in that case, you must have to apply the seasonal ARIMA kind of thing. Now, this slide is most important. That whenever you actually try to apply any kind of statistical model or econometric model, starting from the simple regression to very complex nonlinear model, starting from very simple regression model to very complex nonlinear statistical model, everywhere you have to follow these 4 steps. First is identification, second is estimation, third is diagnostic checking, and last is applications of forecasting. In all the model, you may not use the forecasting because all models are not used for forecasting. Even your objective may not be always to forecast, rather your objective may be to find out the variables which are having significant impact on your response, just like in a regression case. When we actually apply regression model, our main interest is not to forecast, rather our main interest to find out the regressor variables which are having significant impact on the response variable and to quantify that impact. So that's the main aim of the regression variables, though regression model, though we can use that model for prediction purpose also, but not all models are used for forecasting. So first 3 steps will be common for all the models, and if your objective is to forecast also, then you have to go for the 4th step. Okay, so identification, estimation, diagnostic checking, and forecasting or prediction. These are the 4 steps for model building, for building of a model, whether it is a simple model or it's a very complex model. All the cases, it will be remain same. First is identification. I hope we all know this, but very quickly I'll just recapitulate the things that what identification means. Identification means that identifying the variables in a regression setup. I hope you have all done this. Identification means that identifying the important variables to take part in the model. In a regression setup, for example, crop yield. So if you have a crop yield, your response variable, you may have several regressor variables which may have impact on the crop yield. For example, you may include climatic factors, you may include the soil characteristics, you may include the biometrical characteristics of the crop, fertilizer application. Okay, so many factors. Even in the climatic factors or weather variables, you may include maximum temperature, minimum temperature, relative humidity, morning, evening, sunshine hour, wind speed. Okay, there are so many things which you can include in the model which may have impact on the crop yield. But is it possible to include all the factors which has implication on the crop yield in the model? It is not, because if you include more and more factors in the model, more and more variables in the models will become more complex, and it will be more likely that one or more assumptions of the model will be violated, and it will not be parsimonious. So whenever we build up a model, either a regression model or a time series model or nonlinear model, anything, we should be cautious about the parsimony of the model. Parsimony means that the model should be simple as a very containing very less number of parameters, and at the same time, your model should explain sufficient amount of the variability of the response variable. That means in a regression setup, you must have included less number of parameters in the model. Less number of parameters means less number of variables in the model, and your R square or adjusted R square should be quite high. Okay, so these are the two objectives to have a parsimonious model, and to develop a parsimonious model which will be simple as well as explains a sufficient amount of variability in the response variable will be always desirable. So in that, identification is a first important step in model building. So in a regression setup, there are variable selection technique like your forward selection, backward selection, stepwise selection. All these selection techniques are available, and I'm sure that you have all done it. In time series context, identification means identifying the number of lags to be included in the model. If you remember, in few slides back, we have talked about the auto-regressive model of order 1. It may not be order 1, it may be order 2, it may be order 5, it may be order 10 like this. So how to determine that order? How many lags to be included in model? That is identification. Okay, how we'll do that? We'll just come into the next slide. So this is identification. That means identifying the optimum number of lags to be included in the model, or to identify the order of the model. Second is estimation. Once you have identified the model, once you identified the number of lags to be included in the model, then you can write down the functional form of the model, that yt equals to say alpha 0 plus alpha 1 yt minus 1 like this. And once you are done with that, then you can go for estimation of the unknown parameters in the model, and that has to be done by your software. Okay, so there are several estimation techniques like nonlinear least square, maximum likelihood, method of movements. There are many estimation techniques. Generally, nonlinear least square method is used to estimate the parameters of the models. So the software will do the purpose. Once estimation is done, the next important step is diagnostic checking, which is the most important among these 4 steps. Diagnostic checking, or we say the validation of the model. This step actually says about the adequacy of your model, that whether your model which you have built up, whether it is adequate or not, whether it is valid or not. How do we actually go for this? Based on the residuals coming out from the model. Diagnostic checking means once you have done the estimation, that means unknown parameters in the model have been estimated, and so you are now in a position to predict the response variable, because right hand side all the unknown parameters are estimated now, and based on the past values you can actually predict the current value, right, or the future value also. So you have the actual value, you have the predicted value from your model. So you can differentiate these two, whether what is the difference between actual and prediction, that goes to the residual, and the residuals will be examined, the residual will be diagnosed to check the adequacy of the model, or to check the to validate the model. Because if you remember, in any statistical model there is an error term appears. Okay, in any of the statistical model, including time series, you have an error term that is either in epsilon or eta, zeta, whatever, E, whatever symbol you utilize, that error term appears in the model. That is the differentiation from the mathematical model and the statistical model. So in the statistical model, you have an error term, and in mathematical model, you may not have any error term. Just a yes. So, but the error term is unobserved, right? The error terms are unobserved in the model. So when the observations on a factor is unobserved, how can we validate the assumptions mean for that particular model? So this is very difficult. And so that can only be done once the models is estimated, once the prediction is done, and once the residual is found out. That means difference between the actual and the prediction. So on the residuals, we actually validate the assumptions mean for the error term. Once we computed the residuals, then we actually try to validate the assumptions mean for the error term. That means the residuals, whether they are following the normal distribution or not, whether the residuals is having a zero mean or the constant variance or not, whether the residuals are independent or autocorrelated or not. All these things can be examined in the third step, that is in the diagnostic checking. So based on these residuals, we actually validate the assumptions meant for the error term appearing in the model, and also based on the residuals, we actually find out the adequacy of the model. Once we are satisfied in the third stage, then we go for the application of forecasting purpose. In the third stage also, one more thing is done, that is few of the observations is kept for validation purpose. If we have say observations on say 100 observations we are having. So what we do in the first, we just bifurcate the whole data set into two parts. One is called training, another is testing. In general, 70 to 80% observations are kept for training purpose, and remaining observations are kept for validation purpose. So those the validation set is utilized to validate the performance of the model, and we compute several statistical measures, maybe percentage error or mean square error, root mean square error. Like this, there are several statistical measures we can actually compute, and we validate the performance of the model. Now, if we are satisfied in that, then we go for finally forecasting the future observation based on the model we have built up. So these are the four steps in brief, that how these four steps are being utilized during development of this model. Now in identification, how actually it goes on. So first of all, we check the stationarity. If the data is non-stationary, go for differencing or kind of transformation to transform the non-stationary data to a stationary one. Okay. And then two plot we actually look for. One is called autocorrelation plot, and another is partial autocorrelation plot. These are the two plots we will be actually utilizing to find out the optimum lag or initial lag selection process. So autocorrelation function and partial autocorrelation function, they are similar to the simple correlation and partial correlation. Auto only is utilized because we are computing the correlation between the same variables or on the same variables between two lags. So that's why it is auto. And PSCF, that is partial autocorrelation function, will give you the indication of autoregressive lag, and autocorrelation function, that is SCF, will give you the indication on the moving average lag. So this is the two things which we need to remember. PSCF, partial autocorrelation function, will give the value of autoregressive order. Autocorrelation function SCF will give you the value for moving average order. So this from the data we will be actually computing, and we will be determining that what is the number of lags to be included in the model. And then these are some theoretical criteria for selecting the optimum lag. Then once it is done, that order of AR and MA is done, then we go for the estimation stage. Nonlinear least square is used, and we have different criteria for selecting the model. Just like in a regression setup, you know, if we have say 10 regressor variables, okay, and one response variable, so we may find out several regression model. One may contain only one regressor, another model may contain two regressor, like this. So several regressor model can come out, and we choose the best regression model based on the R square and adjusted R square. Similar to that, in a time series setup, here what happens, we have different information criteria like AIC, that is Akaike information criteria, BIC, Bayesian information criteria, there is HQIC, Hannan-Quinn information criteria, SBC, squad Bayesian criteria. Like this, there are several information criteria available, and it will automatically be given when we actually apply the model by using any software package. Particularly in R, we will be using it and we will be visualizing it. Based on the information criteria, we choose the model which is having the minimum information criteria. So it is to be remembered that in case of the regression model, we choose the model which is having higher R square or higher adjusted R square. Whereas in case of the time series model, we choose the best model, or we choose the model as the best, which is having the minimum value of the information criteria. Either you are using AIC or you are using BIC, SBC. Okay, these are the different formula for different information criteria. This is Hannan-Quinn information criteria, HQIC, like this. Okay, and then estimation is done, and then diagnostic checking we have already seen, or we have already discussed that what we do here. Based on the residuals, we actually examine the residuals. We try to plot the residuals, whether it is normally distributed or not, whether any pattern existed in the residual or not, whether the residuals are autocorrelated or not. Okay. Then there are different tests for autocorrelation also, you know, Darwin-Watson test is there, box PR-skew statistics is there. First of all, if we plot the residuals, we may have a guess that whether the residuals is having any pattern or not. If there is a pattern in the residuals, then we can actually see that the model is not adequate. That means some information is still there in the residuals, so it could have been, which could have been extracted by fine-tuning your model. Once the residual is random, once the residual is coming out to be random or independent, then we can ensure that the model, whatever has been built up, that is adequate, because no other information can be extracted from the residual because it has been found out to be random or independent. There is no pattern existed in the residuals. So that's the most important thing in the diagnostic check. And this is a flowchart that once a data is given to you, you go for tentative identification of the data of the order of the model by visualizing the autocorrelation function, partial autocorrelation function, all these things. Then go for estimation technique. Once estimation is done, we go for diagnostic checking. The residuals are analyzed and their validation of the model is being done for the validation set. If the model is okay, that means it is found to be adequate, then we go for the final step, that is using the model for future forecasting. If the model is not found out to be adequate, again we go back to the identification step. That means the lag selection was not proper. Maybe some of the lags variable has not found out to be significant, and still they are there in the model. So it has to be fine-tuned and the model is to be rectified. Until and unless we are satisfied at the validation stage or diagnostic check, where we actually ensure that model adequacy is there, we cannot go further. If the model is not adequate, again we have to go back to the initial stage of identification of the lags, and then we repeat the process. And these are the different statistical measures for validation of the model. Either you go for some percentage error, mean absolute error, there are mean square error, root mean square error, so many things are there. So based on that, we actually validate the models. These are the different application, and we'll be doing this application with a practical data set and giving much more emphasis on the practical part, that how R software package will be demonstrating in R. And it's very easy. You need not to be a programmer to apply the R software package to your data set for forecasting or building a time series model. It's really simple. And beyond this linear time series model, that is ARIMA, if you have other exogenous variable in the model, then you can go for ARIMA X type of model, which is called ARMA model or ARIMA model with inclusion of exogenous variable or regressor variable. For example, if you are modeling a price data, then you know that price is maybe determined or maybe affected by the arrival. So you can include the total arrival in the market as an exogenous variable in price modeling. Similarly, the climatic information also, if you think that climatic information or weather information may have some influence on the price data. So those information can also be included during your model building as a regressor variable or exogenous variable. So in that case, the model will be ARIMA X type of model. In the same code, whatever we'll be using for the ARIMA, in the same code, if we have exogenous variable information, that can be included, and there is no difficulty in getting the output. Similarly, there are some nonlinear model, like if you do not find that your model, the pattern is not basically linear, rather it is non-linear, then you have to go for some non-linear kind of model like autoregressive conditional heteroscedastic model or generalized arts model. These are the different non-linear time space model available in the literature. And of course, in the recent time, there are machine learning techniques which are also being used rigorously to predict some of the time series observation that can also be used. Okay, and yeah, I think this is the theoretical part for the time series model, and we may go for the practical part, and after that we'll be having a brief discussion on the panel, including its practical. So up to this, if you have any query, any specific observations, you are welcome to ask. Otherwise, we'll be just share the R code, I mean R Studio. Yes, there is some sound coming up. If you can mute.
Chandresh Gularia. Chandresh, please mute yourself. Chandresh Gularia, please mute yourself.
Yeah, it is mute.
Yes,
Okay.
now mute.
Okay, so we'll just start a fresh R session. So this is a R Studio. I'm sure that you are all comfortable with this. You have used this R session, and so this is R Studio. Whether you are using simple R or R Studio, it is one or same thing. There is no difference. Only difference is that visualization part. In R Studio, it is easy to visualize because in the same window we have 4 small windows. We can write down the program. We can see the output in the same window. We can see what are the packages being utilized and what are the variables and data sets are being created on the on this particular R session. Those can be visualized in the same window. So if you want to practice with me, those who are having a system, you can do with me, so that if you have any difficulty in implementing the particular code or particular line or execution of the line, you may ask and you may clarify it. So a very common data set, I'll just use yeah, sorry, just a minute. I'll again share the whole screen. So we have a data set, any of the time series data you can use. I have a data on food grain production data, or any time series data if you have on that particular data also you can use it. So this is the data. I hope it's visible. The data on food grain production, this is starting from 1950 onwards up to okay. So this data set I can share in the chat box also, if I can share to all the participants. Can I share it? Everyone, yeah. So I just share this data set. Just a minute. Yes. Oh, I think there is some Purgana cannot be sent. It is currently in use. Okay, I'll just close this first, and then yeah. Now this data is shared in the chat box, so you can download this data, and those who are interested, you can do the practical part with me so that if you have any doubt, you may clear it. So again, I am just opening the data. Yeah, this is the data set, and we have a variable year and the production. So here, this is just to demonstrate, this is just to indicate that the production 50.83 million ton is the food grain production in 1950. That's it. So the data set is up to 2019. This is the data set, and that means total 70 observations are there, 1950 to 2019. Total 70 years data is with us. Now, what is next? First of all, we try to visualize the data, because whenever a raw data comes in our hand, we first try to visualize the pattern existed in the data set. So simple, we just draw a scatter plot or line plot from this data. I'll just draw a plot. This is the plot, that production data, and if you just if you select the year data also, horizontal axis, you just select this, and this is the pattern. So production, food grain production data starting from 1950 up to 2019, and this is the pattern. This is almost linear over the year. So if you draw a trend line over it, add trend line, and you will find that the observations are almost lying along this particular straight line. Okay, so it ensures that the linearity of the pattern, the linearity of the data over time point. The second assumptions, if you remember, for time series is the stationarity assumption. Now here, this is a single response variable, that is food grain production. Okay, and now you may ask the question that if we have a single variable, like say y, we have a single mean, we have a single variance, so obviously it will be constant. But we are saying that the mean and variance and also the autocovariance and autocorrelation would be constant throughout the time point. How it is? When we say this, that means the whole observations, we have 70 observations, and we can divide these observations into small subset, say five observations. And we compute the mean, we compute the variance. And we see that whether the mean is constant for all the set and the variance is also constant for all the set or not. Here, very clearly you can see that mean is increasing, almost a monotonous increasing function over time point. You can see during 1950 to 1955, say, the mean of the, average food grain production was around, say, 52 million ton or so. But after that, as the time progresses, the food grain production is increased. That means the mean is not constant. Similarly, the variability, you can see there are some time epochs, there are some year. For example, if you follow my cursor, say 2002, the food grain production dropped to 174 million ton with respect to its just previous year. That is 2001, where it was 212 million ton. So this particular region, there is a variability. The variance is high. Whereas in other region where there is no variance or no variability, that means the variability is not constant throughout the time point. So both the mean as well as the variance is non-constant throughout the time point. That means the stationarity assumption is violated. So until and unless you transform this data set, you cannot apply the model because your assumptions are not valid. Okay, so once you plot the observations or plot the data, we can actually guess several things. Whether about the assumptions, about the pattern existed in the data, about the model to be initially called for to apply on this particular data, all these things can be gauged once you actually visualize the data set. So this is very much mandatory that you visualize the data first before you actually apply the model to your data. Now go to the R session. So this is the R Studio, and if you have any issues here, let me know. So first of all, we'll be just importing the data. We have a CSV file. R can handle CSV or Excel file or TXT, that is text file, any file. Okay, in general, we use CSV or Excel file for storing our data set. In this particular data, whatever I have shared also, that's your CSV file. How to invite a particular, also how to know which package is required for it. I'll answer this. So first of all, let us import the data. So for importing the data, you know, these are the steps. We just give a data set name and followed by equality sign. So less than and hyphen, this combination is just a equality sign. You can give equal also. And whatever we write down in the left hand side of this equality sign, this is the user defined variable name or user defined dataset name. And whatever we write down in the right hand side of the equality sign, that is the R keyword or R functionality. Okay, so we have a CSV file, and you know the reading and writing. So importing means read and export means write. These are the two keywords, very easy to remember. If you want to import a data set, you just call read, R-E-A-D, read. If you want to export the output, you just write down write, W-R-I-T-E, write. So read, and we have a CSV file, so read.csv. Within bracket, there are several ways to import the data. First of all, you may specify the full path of the data, wherever, in which drive, in which folder you have kept the full path of the data, you can copy and paste it here, or you can write down simple file.choose and then bracket. And if you run this, then a small window will appear, and through using your mouse and keyboard, you can go to the desired drive to pinpoint your data, and then you can attach that particular data to your current R environment. So this is the way, whatever way you find comfortable, you can use that particular way. And the better way to write down the program is that after this, you just write down the header equals to true, because in almost all the data set in Excel or CSV, whenever we prepare our data, the first row we keep for the labeling of the data, heading of the variable, the name of the variable. So by default, it will be true. So I run this particular code, and so this particular window will appear. Once you run this code, this window will appear, and you go to the desired drive wherever you have saved your data set. So I go to the desired drive, and so it is taking a little time to so there is a food grain production data somewhere. I'll just see food grain production. Yeah. Okay, I think it is done. And then once it is done, you just attach the data set. So my data is the data set which I have. My data is the data actually where I have stored the data set. And then attach statement means we are attaching this data set in the current R environment, which necessarily means that whatever variables are there within my data, those variables are now accessible by their name. So once I have done this attach statement, that means in my data, there are two variables you have seen. One is year, another is production, PROD. So both these variables are now accessible by their name. I have done this attached. Now the data is clean. Data is ready, and it has been imported successfully in the R environment. And if you just print the data, select the my data and print it. You just run it. So you'll see that the data set has been imported year and then PROD production. Okay. Now we will be only using this variable PROD production, because year is not a variable. Basically, it is used for just to indicate that this production is for this particular time point. Now, what is the first step? First step is the identification in case of the model building. And what identification? What do you mean by identification? It means that identification of the lagged variable. Okay, so how do you do that? We go for two plot. One is called ACF, that is autocorrelation function plot. You can make a comments that say plotting ACF, that is autocorrelation function. How do we plot it? Simply write down ACF. ACF, all in the small case. ACF within bracket PROD. Because PROD, this production is the only variable on which we will be developing the model. So we just call the function ACF, that is to plot the autocorrelation function on the production. Enter it and you will get this particular plot of production. I think you can see this. This is the ACF plot. Okay. And these ACF and PSAF plot also will help you to validate or to examine the assumptions, whether they are satisfied or not. So if you can see, if you can have a closer look on this ACF plot, you can see that the autocorrelation function decays very slowly. First autocorrelation function at the 0th lag, it will be 1. 0th lag autocorrelation means YT versus YT correlation. So it will be always 1. Starting from 1 lag onwards. So 1 lag autocorrelation, you can see it is close to 1, maybe 0.97 or so. Second lag autocorrelation, little less. Third lag, like this. The autocorrelation is decaying over the lags, but the decay rate is very slow. If it happens, if the autocorrelation function plot looks like this, it indicates possible non-stationarity in the data. You need not to go for any statistical test. If your plot looks like this, that means autocorrelation decays very slowly, or there is a very slow hyperbolic decay of the autocorrelation function, then it indicates that there is a possible non-stationarity in the data. Understand? Similarly, you can go for PSAF, plotting ACF, and then same comments I can put it here. When I say it is a comment, that means it is not a part of the program. It is not a part of this our program line. I just write down PSAF within bracket PROD. Okay, and same. So this will be your partial autocorrelation function plot. This will be your partial autocorrelation function plot. Okay. Now, what this plot indicate, or how we actually find out the lag from this plot? If you remember, during our discussion, we have told that partial autocorrelation function plot will help you in identifying the order of autoregression, lag of autoregression. So you can see that there is a dotted line just parallel to your x-axis. Blue colored dotted line parallel to x-axis you can visualize, and that is the critical region. So if any of the spike is going beyond that critical region, if any of the spike goes beyond that critical region, it is significant. That means that autocorrelation or partial autocorrelation is significant. So here you can see only one lag is significant, remaining all are not significant. That means for this particular model, if you want to choose the autoregressive lag, it will be 1. Partial autocorrelation function will give you the autoregression lag, and it says that it is 1. Though it is not final, because this is not a stationary data, right? We have seen that the data is non-stationary. So then we go for checking the stationarity and non-stationarity. And for that, you need to install a package called T-series. T-series is a R package for the time series. And how to install, I think you know, you go to this fourth window called where you can see file, plot, packages, all this thing. You click on the package, click on the install, write down here the name of the package T-series, okay, and then you install it. So it will be installed in your system. Installation of the package is one time, whether loading of the package is every time. If you install a package in your system, it will remain there until and unless you format your system. But every time you open your R Studio or R, and if you want to call for any function from that particular package has to be loaded first. So this library within bracket T-series, if I give, and if I run this, that means I am loading this package. So this package has been loaded. Okay. And now I can call the functionalities which are there under this package T series, and we can apply on our data. So I just write down checking stationarity or testing stationarity. There are several tests. If you remember, we call up Dickey-Fuller test, augmented Dickey-Fuller test, Phillips-Perron test, KPSS test. There are several tests available for testing the stationarity. So their functional name ADF.test. So like this, PP.test, KPSS.test. So these are the function for testing this stationarity. ADF.test. Within bracket, I just write down the variable name, that is production, PROD, on which we are applying our model. So ADF.test within bracket PROD I put, and I run it, and in the console you can see that this test has been applied, augmented Dickey-Fuller test, and this is the test statistics value. This is the lag order for the DF test, and this is the p-value, that is 0.77. And whenever we apply any test, that means we are using statistical test, testing of hypothesis. So it must have a null hypothesis, it must have an alternate hypothesis. So here in case of ADF test, you can see alternate hypothesis is given, that is stationary. That means null hypothesis was non-stationary. And what is our p-value? You can see p-value is 0.77. What does it mean? That means the test is not significant. 0.77 p-value, it is compared with the level of significance, that is 0.05, that is 5% level of significance. So this p-value is greater than 0.05. It means that the test is not significant. That means we do not reject the null hypothesis. What is our null hypothesis? Null hypothesis is the data is non-stationary. That means this data set PROD is non-stationary, and we have also seen it through the plot and also from the SCF plot. So what we do, we have to transform this data, and then only we can proceed. So for transformation or for differencing, I'll just put say differencing the data. How do we go for differencing? So I can put a new variable, say PROD1, which is equals to DIFF is the keyword for differencing the data. DIFF. Within bracket, I put PROD production, and I run it. So PROD1 is my new variable, which is the differenced data. DIFF is the keyword for differencing the variable. Differencing means the difference between the current and the immediate past. Difference between the current observation and its immediate past observation. And then again on this newly transformed variable, we will go for testing ADF test. Say for example, again I put ADF test, ADF.test within bracket PROD1. Okay. Now here you can see, once we are done, once we have transformed the data, the variable by differencing, and we have tested the stationarity on the differenced data or the transformed variable, we find the p-value is now 0.01. That means your null hypothesis is rejected. That means alternative hypothesis, which is stationarity, is accepted. So after one differencing, the data has become stationary. Now this data is ready for further modeling. Okay. So this is the way we check. Similarly, there is a PP test, KPSS test you can try. You just, instead of ADF, you put PP. Instead of ADF, you put KPSS. All are in the small case because R is case sensitive software. Okay. It can differentiate your lowercase and uppercase. Now, once it is done, ADF test and testing the stationarity, next we go for identification. So again, I plot SCF on the difference variable now, on the transform variable. Now check this SCF. This SCF you can check, and you can see first is for the 0th lag, you can omit it, you can just ignore it. You start from the first lag onwards. So one lag is significant, other are not significant. So what SCF gives you? SCF gives you the order of moving average. Order of moving average. So order of moving average is 1. Clear? Similarly, we plot PSCF. And here you can see what is the fate. Here the first is 1, not 0. You can see 1, 2, 3, 4, 5. So first lag is significant and fourth is significant. So we can start from the maximum. That means the AR order is 4. And all combination of the order we have to run, and based on the information criteria, we need to select the best model. So that is the main step for model building. Though we do not do it, we may go for automatic model selection process also. But if you want to do stepwise kind of thing, then this is the way that you first see the ACF, first and see the partial ACF and select the maximum lag or initial lag. So ACF has indicated that moving average order is 1. PACF has indicated that autoregressive order is 4, because 4 is the maximum lag where it is significant. Okay, so 4 and below, all lag combination we need to try, and we need to select the best model based on the AIC criteria or any other information criteria. So we have seen now, we have selected the identification, we have identified the initial model, that AR order is 4 and MA order is 1, and we can run the model. So for building the model, that is the estimation of the parameters in the model, we need to load one more library that is called Forecast. Forecast is the package where the different functionality of building the model and checking the accuracy and diagnostic checking, all these are available functionality. So Forecast package has to be installed, as we have installed the T-Series package, and then once it is installed, then it has to be loaded in your current R environment. So I load the Forecast package. It is now loaded, and then we can actually go for calling the model. The model is ARIMA. Basically, we can give a particular name of the model also. Say I put model equals to ARIMA. ARIMA is the keyword or functionality, R function, ARIMA, ARIMA. Okay, within bracket, our data set, our variable is production PROD, not PROD1, because we will be denoting the differentiation option. So original variable PROD on which we will be working. Then we put the order. Order we have already found out, initial order. So order equals to C within bracket. There are 3 arguments in the order. First is AR order, which is 4. Second is D for differentiation. That is 1. One time differentiation we have done. And MA order is 1. So 4, 1, 1. This is our initial model. 4, 1, 1. And then if you want to have an intercept to be included in the model, so I put include dropped drift equals to true. So this is the complete code for building a ARIMA model, though there are several other arguments which can be passed through this particular function, but they are not necessarily to be passed on. We can go to the help and we can see that which argument does what particular things and what output is being generated if we give that particular argument. So we can explore it and we can see that what is the difference. So this is the initial model order we have selected 4, 1, 1. We have included the intercept term in the model and we have called this particular function called ARIMA. Now we have run this and this has been successfully executed, you can see. Okay, and you just here you can see the model, or you can see the summary or model output, summary of model, and this is the summary of the model. So here you can see AR order was 4, so AR1 coefficient, AR2, AR3, AR4. MA order was 1, so MA1 coefficient, and drift is for the intercept term, and corresponding standard error is given. So this is the coefficient, corresponding standard error is here. This is the coefficient, corresponding standard error like this. Okay, and the information criteria, AIC, AICC, BIC, log likelihood, these are given, and the training set for this particular data set we have been given with the different validation measurement: mean error, root mean square error, mean absolute error, mean prediction error, mean absolute prediction error, like this. Okay, so all these particular statistics have been given with, and you can actually choose that whether this particular model is good or not. Now, one thing which we need to see is that the coefficients, their corresponding p-values are not given. Only the coefficient along with its standard error is given. So coefficient and its standard error. So from here we can get the t statistics, coefficient divided by its standard error. And if this t statistics is greater than 1.96, then we can say that it is a significant coefficient. First one, say 0.43 divided by 0.33, 0.19 divided by 0.23. So I think most of the coefficients are not significant here. And that is utilized in fine tuning your model, because if you remember, we told that this is the maximum lag order we have included, and beyond or below that, all order combination we need to run. So 4, 1, 1, the middle value 1. This is for differentiating. That will remain fixed. Only the AR order and MA order, that will have to be changed, and we have to run different models. So this is one model, and we have seen the AIC and SBC. So now I run 1, 1, 1, 1. See the summary. You can see here, AR1 is not significant again, but MA1 is significant. What is the AIC? 526 here. Earlier it was 528, little less. Now I put AR order is 0, only MA order. And I go for seeing the summary. Here you can see MA order, only MA model was applied, and it is highly significant because the ratio 0.65 divided by 0.08. It is almost 8. It is highly significant, and AIC is also 524, minimum among these three. Earlier it was 526, and before that it was 528, like this. So all these combinations of the models you need to run, and we have to see, or we have to check the information criteria and also the significance of each of the parameters, and we need to choose the best model based on the minimum information criteria. Okay. So this is the way, and instead of doing this manually repeated time, we have a particular function which will do all these things automatically, and you can build up your model. And that function is called AutoArima. So auto.arima. This is a function in R under the package forecast. Auto.arima, within bracket you can give the variable name, and everything will be done. So I just put a separate name, say model 1. Auto.arima, within bracket I put production PROD, and if I put trace equals to true, that means whatever models combinations are being applied, all those model combinations will be given along with the information criteria will be given. Okay, so I'll just run it, and you will see that these are the different model combination. ARIMA 212, 010, 110, 011, 010, all these combinations have been built up, and you have been given the best model as ARIMA 011 with drift. Drift means intercept. So for this particular model, you have the information criteria as the least one. You can also check 011 with drift. This is the model. 525 is the information criteria. So this will be given by auto.arima. Okay, and so this is basically the process. But here what we have not done is that at the first stage we need to bifurcate the data, training and testing data. So out of 70 observations, we can do now also, there is no problem. For example, I can make a train data. Train is nothing but, say for example, our data set is my data. If you remember, the original data is my data, where I have stored the data set. And in the my data, the second column, that is the production, is in the second column. So from this my data, I just put say 1 to up to say 65. First 65 observations I keep it for training. This is for the train set. And similarly test I put my data and 66th row to 70 and second column. This is for the test data. I think I need not to explain what we are doing here. Train is the data set which I am creating from my data. My data is the data set where I have stored the data during importing, right? In my data, there are two columns. First column is year, second column is production. We are only concerned about the production, second column. So 1 to 65 is the row number. This is a kind of array, the row argument and then column. 1 to 65 is the row and second column. I am extracting and keeping these in the train data. Similarly, 66 to 70th row, last 5 observations, I am extracting for the second column and keeping it in the test data. So train and test I have created now. Now we'll be modeling, say I'll put model 3 equals to, I call AutoArima, auto.arima within bracket train. Now train is a single variable model because we have extracted the second column and stored it in the train. So auto.arima on the train data set I put, okay, and I put trace equals to 2. So this is the model. 011 is the model. Here you can see the AIC information also. So this is for trace, right? And then I go for forecasting also. I go for forecast. So forecast equals to, say forecast within bracket model 3 and H equals to 5. H means that what is the number of step ahead you want the forecast. So I forecast for the 5 step ahead because in the test data set we want to validate the model. That is why whatever model has been built up for the train data, the same model I will be using to forecast for the next 5 observations, and the next 5 observations are there in the test data set, and we'll just validate those. We'll just tally that how close my forecast is with actual. So I run this, the forecast has been obtained, and if you just put the accuracy measure, accuracy, this is a similar function, I put forecast and then the test data. So you can see both training as well as test data you have been given with the accuracy measurement. Mean error for the training set, RMSE root mean square error for the training set, root mean square error for the testing set. Okay, we are basically more concerned with this MAPE. This is the most important statistics which we actually report during our analysis. This is mean, absolute, prediction error or percentage error. Training set, we have got 5.93% error, around 6% error in the training set, and in the testing set we have got 5% error. So 5%, 6% error is in the acceptable range, very much acceptable range, and we go for this particular model, using this particular model for the future forecast also. So this is the way you can go for utilizing your model for future forecast. Now, once you are satisfied here, then the same model will be utilized, and you just give the steps ahead. You change the steps, say 10 step ahead, 15 step ahead. Like this, you can put and you can get the forecast for the future values or future observation. That's it. Now, once you are done with this model estimation, then validation or diagnostic checking also can be done, and it can be done by extracting the residual. So I put residual to extract the residuals within bracket model 3. So for this model 3, whatever with the model we have developed, we can extract the residual, and on these residuals we can actually check whether the residuals are following the assumptions of the error term or not. So for example, for the normality checking, so I put Sapiro will test Sapiro dot test. That is Sapiro will test for testing the normality. You can apply any test, Kolmogorov's-Smirnov test, Anderson-Darling, Von-Mises, chi-square. So many tests are available. Any test you apply for checking the normality of the residual. So I put this residual and I can find that this is the test statistics value. Similarly, you can go for the independence of the residual, or you can simply plot the histogram kind of thing, hist of residual, and this is your histogram. Okay, so this way you can diagnose the residuals and you can go for finding out the adequacy of the model. Okay, so I think in nutshell, this is the linear time series or ARIMA kind of thing. If you have any query or any question, we can take up those questions before we go for the next, that is panel. I'll take few minutes for panels. So in ANIMA, actually, we do not use Excel to fit the ANIMA model. In Excel, whatever we have done, that is to visualize the data set in terms of plot, and we have done that. And the same thing after that, for following the different steps in model building in R, we have demonstrated. And if you have any issues here, those who are working with me, those who are running this particular code with me, if they face any issue, you are welcome to ask those and clarify your doubt. Any question? Can once again explain how we select 411 from the graph? Yeah, sure. So 411, how we selected the first initial model. We have, first of all, we have differentiated the data because the first data set was non-stationary. That's why we have differentiated the data, and after that we have checked the ACF and PACF on the difference data. So PACF on the difference data, that is production one. Again, I am running it, and you can see here.
Shweta, please mute yourself.
So this is the PACF, and you can see the number of lags, the maximum lag you have to see. There are two ways. Some scientists look for the number of lags. For example, here 2 lags are significant. First lag and fourth lag. 2 lags are significant. So you can choose the AR order, that is p value is 2. And some group tells that maximum lag, you consider that lag. So here fourth lag is the maximum where it is found out to be significant. Okay, so you can choose 4. Either you can go for 2 or we can go for 4. Better to go for the higher thing, because below that all combinations will be trying and will be choosing the best one. That's why you have selected 4. You can go for 2 also. That's also valid. So this is PACF, autoregressive order selection. And if you just plot ACF, that will give you the moving average order selection. So moving average order selection, here also again the same thing. First is for 0th lag, so you need to ignore that. And the next onwards, only 1 lag is significant. So that is why moving average order is 1. This is significant because this is crossing the critical region. This dotted blue colored line parallel to x-axis, this is your critical region. Any spike, any correlation beyond that critical region, either upper side or lower side, it will be significant. And from there, we have just selected 4-1. Okay. Hope you understand now. Someone has written ARIMA is not working. You just check the spelling, capital A in the forecast package. When we call for the ARIMA model, the spelling A is in uppercase and RIMA, they are in the lowercase. Object PROD not found. So if you have not attached the data set, this production will not be found. You have to attach this data set, my data, then only PROD will come. Also, the other way is, instead of PROD, you just put my data. If you have given the same data set name, within bracket, comma, and 2, second column. If you face the same issue, even after attaching the data, then you can go for alternate use. You just put the my data statement, third bracket, a comma, and second column. It means that we select all row, but the second column. Second column is the production. Okay, please try and it will be solved. Any other question? No. So quickly we'll just see the panel. Quickly we'll be just seeing the panel, and only 2-3 lines code for running a panel model, whether it is fixed effect model or random effect model. And so I have the presentation also. I will share this, although I will not use this now. Panel, the basic idea is that, we have a time series. Now, by now you understand what is the time series. Time series means the observations on a particular variable is collected over time point or equally spaced time interval. That is the time series, right? So ordering of the observation has meaning. And there is a cross-section data. Cross-section means, what is a cross-section? Cross-section means that you collect the observations on a variable over the different locations or over the different space. So that is a cross section at a particular time point. So cross sections means at a particular time point, we collect the data set on a variable over the different location. Time series means we collect the variable observations on a variable in a particular location over the time point. So that is time series. If you combine these two, time series and cross section, then we actually come with the panel data. That means panel is having two dimensions. One is a time dimension, another is the cross section or space dimension. That means if I give you the example, for example, the rice yield in different states of India over the last 20 years. So this is a panel data. Rice yield in different states of India over the last 20 years. So different states is the cross-section dimension. Over the time point 20 years, that is the time series dimension. We combine these two and we come up with the panel data. And when we are having this, we have several advantages of this. First of all, we have the large number of observations we will have because we have both the time dimension as well as the cross-section dimension, and the number of degrees of freedom will be sufficient to for the model to be applied. Okay, it is better suited for dynamics of change, to study the dynamics of the change, and the measures or the effect which are not detected. Using the pure time series or pure cross section, it can be studied well using the panel data. So likewise, there are several advantages of this panel data, and one data set which we will be using, it is available in the R also. That is the Grunfeld data, which is I think it is available in any of the econometrics book also. On this particular data, we will be just trying few lines R code to estimate the panel model, both the fixed effect as well as the random effect, and whether to go for random effect or fixed effect model. There is a test called Hosman test. That test will also see that which particular model is to be utilized. And there are several dimensions of estimating this panel model by introducing the different dummies. For example, if you want to see the individual time series effect or time point effect, you include the time dummies. If you want to see the cross-section effect, individual location-wise effect, then we can include that location-wise dummies in the model to estimate the different effect, and likewise. So basically, there are two effects. One is a fixed effect, another is your random effect model. So in the fixed effect model, there are these four variants. All coefficient we can consider as constant. That is kind of pool model. Then second option is you just vary the intercept term, keeping constant for slope coefficient. Third is you intercept varies over individual as well as time, and all coefficient varies. So these are the different variation of the fixed effect approach, and we can go for the different variants to estimate the individual effect, and its significant or not significant test also we can do. Okay. Similarly, there is your random effect approach. In random effect approach, the intercept is not fixed. Basically, we consider that this is also a random, and accordingly we build up the model. And this is the random effect model, where we can have two error term, basically epsilon and VIT. I think in any of the textbook we can actually look for this functional form of the model and estimation purpose also. These are the different assumptions of the random effect model. Okay, so we'll be seeing in the next 10 or 15 minutes that how actually we can apply this model to the data in reality by utilizing the software package. And then obviously that whether we should go for the fixed effect model or random effect model or ECM, how to judge that. For that, there is a specific test called Hosman test, and that test is to be applied to check for that which particular model is to be utilized for the data under consideration. Now going for this, so yeah, just a minute, give me a sorry for the disturbance. So in the panel model, we have a data. Again, the data set, the same data, though it is available in the R also, in the R help Grunfeld data. And just to see that what is the data. Yeah. So this is the data set. And just again, I'm sharing this data with you. So year, investment, and then I think this farm value and capital. These are the three variable basically, and year. And we have how many farm? There are 10 farms. So the data set consists of 10 farms and how many years? It is 1935 to 1954, 20 years. 20 years time and 10 farms, 3 variables. One is response, that is investment. This is farm value, I hope, and this is capital. So these are the 3 variable, and this is the location dimension, cross section dimension, and this is the time dimension here. This is the variable. Okay. So I will share this with you to everyone. Computer. Yeah. So this is the data I have sent. Okay, and we go to R. So here in another R script, we can write down this. So again, same thing. We just import the data set. You can give any name. Either earlier we have given a my data. Now also we can give my data or any other name. It is better to use. So I put say Grunfeld, the same data set name. Okay, equals to your read.csv, same code, read.csv within bracket, file.choose you can put, or you can put the path, and then header equals to true. So this is the way to import the data set. Go to drive, wherever you have saved the data, you go to that particular drive, and then you select the data. So I have selected it, and now I attach this attach statement, Grunfeld data. So I am done. Okay, that data set has been imported, and if you want to see that data, you just print that data set, and this data will be printed in your console. So these are the variables. First of all, first is the farm data, 1 to 10 farms, then 20 years data, then investment, farm value, and capital. These are the 3 variables. Okay, these are the 3 variables. We got it. Now, what to do next? Next, we have to apply the panel model. For panel data set, we have a library called PLM. We have a library called PLM, panel linear model, PLM. This is a library. This package PLM has to be installed, as we have installed the T-series earlier. The way is the similar. And once you have installed it, after that you have to load this package by calling this library within bracket the package name. So I have already installed earlier, and now I have loaded the package in this current R environment. Now, fixed effect model, that means within model, and then the random effect model is there. So for example, I put say Grunfeld dot fixed effect. Okay, this is a output variable name only I'm giving. You can give any name. Whatever we write down in the left hand side of the equality sign, that is the user defined variable name or output dataset name. And whatever now you will be writing after the in the right hand side of the equality sign, that is the R function or your created function. So PLM is the function itself, panel linear model, and then giving a response variable first, that is dependent variable is I, investment, equals to, here equals to means this curl symbol, just like regression, you have run the regression model, and then we put the two F and C, these are the two regressor variable, farm value and capital, so F plus C, and then I put data equals to, we have used the Granfield data. So this is the data set. And then model equals to, I put within. That is fixed effect model. And this is the option. That's within variation, between variations, two ways, all these different kind of model you can run. So this is one model. So I can run it. This is executed. Okay. If you want to see it, you just put summary of done.fe. So this is the model estimate, kind of regression, simple. So F, C, these are the two coefficients. Okay, they are highly significant, and corresponding R square, adjusted R square, and overall model significance they have been given with. Now, check for this individual effect, whether the cross section effect and your time series effect or time dimension effect, whether they are significant or not. So for that, we have the test, like say, we can go for fixed effect test. Within bracket, your model's output statement, grant.fe, fixed effect model. Okay, and then your effect is individual. Individual means the form. Individual. And you can see you have 10 forms, and all the forms, the effects are given. Okay, that means intercept. Because if you want to vary the intercept across the form to see the effect of individual form, those many dummies will be incorporated and the effect will be estimated. Then you can see that whether this effect is significant or not. For example, your time dimension effect or individual cross section effect, whether they are significant or not. For that, we have a test called this test, I think it is PF test, F test, kind of F test. So PF test, within bracket, your model output name, and sorry, this is PLM test. PLM test, this is actually called Bruce-Pagan test for testing the significance of effect, whether the cross-section effect and time series effect, they are significant in this. That means whether you need to use the panel model or simple pooled kind of regression model. So to test that particular thing, and then you can put here effect equals to say individual. And here you can see this is the test, and you know, individual means your cross section effect. Okay, and this is significant because your p-value is 2.2 e to the power minus 16, which is very much close to 0. Similarly, instead of individual, you can put say time, and your time effect is not significant. Here you can see the p-value is 0.99. So though your individual form effect is significant, but your time dimension effect is not significant. So it will actually indicates you that if you want to apply this panel model, you include the cross-section dummies, but not the time dummies. Over time, there is no significant effect. So this is actually kind of prerequisite before you actually go for finding your model and seeing the estimate. Okay, and then similarly, if you go for the random effect model, so I just put say run.random effect, same thing only, PLM test, PLM within bracket, your I equals to F plus C, data equals to Granfield. Okay, and model equals to, you put random. So this is, sorry. This is a random effect model we have run. Okay, and now we can see the random effect model estimate also by going to the summary and then putting the output of this model. So this is your random effect model estimate and the corresponding parameter estimate. You can see corresponding to A, C, they are also significant. And overall model is also significant. And then if you want to test that whether this random effect model or fixed effect model is to be used, which model is to be chosen. that by utilizing your Hostman test, that can be tested by using pH test. That is called Hostman test, pH test. All are there in your PLM package. So I put the output of both, that is fixed effect as well as random effect, to compare. Okay, and here I can see p-value is this. So alternate hypothesis, one model is inconsistent, that is the random effect model, the latter model is inconsistent, and this is alternate hypothesis. So p-value is 0.3119. It means that the test is not significant. That means null hypothesis is to be accepted. It is not rejected. And null hypothesis says that your random effect model is to be used. Either alternative hypothesis says that random effect model is inconsistent. So in this particular scenario, you have to use the random effect model, and that particular random effect model estimate, that summary within bracket grunt.re, that model estimate you need to report. Similarly, there are several other tests also to test for the individual effect. We have just given the demonstration of 2-3 tests, like whether the fixed effect, individual effect is significant or not, whether the time domain effect is significant or not, and also the Hostman test for testing the for choosing which particular model is to choose, fixed effect or random effect, like this. Ultimately, this is a kind of regression. So if you know the regression well, and if you are well versed with the regression model, panel is kind of a regression only. Only thing is the difference in the assumption part, the error part, the intercept or the coefficients, they are not fixed here. According to the situation, for example, here individual effect are coming out to be significant, though time effect is not coming out to be significant. So individual effect, you need to incorporate the dummies for individual location or individual farm, and we have to estimate it. So this is in nutshell, and this is the simple code, 2-3 lines code only, not the big thing. But for more explanation and more the options, you are advised to go for this help page. Go to this help PLM. You just go to the package PLM. Then here is the help for the PLM, and for different function. Say if you go, this is the alphabetically the help function it is given. Go to P and go to PLM. These are the different options you can actually choose. Formula, data, subset, weight. These are the different effect, individual, time, two-way, nested. Okay, these are the different model option, and these many options are given with example also at the end, that how to run, how to incorporate those argument in the model option to finally get the output. So this way you can actually explore it, and you can get much more idea on it. And if you face any issue, that are also through email, you can communicate and would be ready to help if you face any issue. Any query, any question? I think we have already come to the lunch time. So participants, no, they are there. Well, any question, any query, any clarification you want? Otherwise, we may stop. Yeah, sure, you will try the analysis, and if you face any issue, you are welcome to communicate.
Thank you, sir, for giving information.
Yes,
Sir, Santosh here. Hello.
yes, Santosh ji, boliye.
Sir, I have one clarification. This you have taken different place data and different panel, like different location or space place data over a particular year.
Yes.
So can you take in this model? Can you take different year in the different places at a time? You cannot take, sir.
The two ways you can give. So option is the two way.
Okay.
So we have given the within effect in the model option. You
Yes.
can have your two ways option. So their cross section as well as your time dimension, both will be incorporated.
Okay. Okay. Up to 2 years you can take, sir. 2
Yes,
points.
yes. Yeah, you can do that.
Okay, sir. Thank you.
Sir, there are some questions.
Yes, yes.
The first question is from Dr. Ganga Devi.
Haji.
How the negative value of intercept is interpreted?
Negative value of intercept. Intercept is, I think, in a model, in a regression setup, this is a regression. So in a regression setup, how we interpret the intercept. So here, in case of the this particular data set, where the response variable is investment, the intercept may not be negative, but it should be. We can look for the significance of that intercept. It might be not significant. So if it is coming out to be negative, it should be 0. So we can infer that it is not significant from 0. So it is basically 0.
And another is, if intercept is significant, then what it indicate?
Yes, if intercept is significant, that means if you put the values for other regressor variable like your f and c as 0, then also you will get some values for the response variable. So that is the meaning of intercept. It is same just like in a regression setup also. For regression, for example, crop yield is your dependent variable or response variable, and you have several other regressor variable. Now, if you do not put any rainfall, for example, still you can have some yield. That is your intercept. If I build up a model that crop yield is dependent on rainfall. Now, if I put rainfall as 0, then it does not necessarily mean that your crop yield will be 0. It will be something. So that something is the intercept.
So the next question from Ratika Sharma. How to invite a particular package in R?
How to?
Invite a particular package in R.
I think it is invite. I think it is install. Invite, I don't know. It is to be installed. So if I have already demonstrated like T series and forecast and other packages also, you go to the package. There are two options, install and update. Click on the install and then you write down the package name and install it. So very easy.
How to know which package is required for which analysis?
Yes, that's very crucial question, very important question. There is no straightforward answer because you need to search it. For a particular analysis, there are several packages. A particular analysis can be done by using several packages. So you need to Google it. For example, I want to run a panel regression model using R. So you simply write down panel regression in R. You will be demonstrated with the PLM package. There are other packages also for running a panel regression. So accordingly, you have to choose. There is no, I think, straightforward answer to this particular question. You need to search it.
And another question, what is the difference between R2 and adjusted R2?
R square and adjusted R square. It is a question in the regression. So R square and adjusted R square, it should be utilized for choosing the best model in the regression setup, right? You know that in a regression model, if you have different number of regressor variables, your R square and adjusted R square will be changed, will be different. So in that case, for comparing the regression model having different number of regressor variables, adjusted R square is to be utilized. For example, 10 regressor variables are there. You can build up 10 regression model or even more regression model. And if you want to choose the best regression model out of those, then you should go for adjusted R square, because adjusted R square is adjusted for degrees of freedom in the model. R square is not adjusted for degrees of freedom.
And sir, another, which R version is best?
Which
R version is best.
Obviously the latest version will be the best. Whatever latest version is utilized, the released, that version will be the best, because all the packages will be updated there and new functionalities will be given there. So better to use the updated version, the latest version.
Okay, sir. I think there is no any query. So thank you, sir, for giving your valuable time to us. And we will contact you if any query occur by our participant. Thank you.
Sure. Anytime and every time you are welcome to clarify your query. I will be happy to clarify. Thank you, Dilip. Thank you, Rajni ma'am. Also, thanks Niap for giving me this opportunity to discuss the things with the participants. Thank you all.
Thank you, sir.
Thank you.
Hello, everyone. The next lecture on economic of marine fishery in India by Dr. S.S. Raju at 2:30. So kindly join everyone at 2 p.m. Thank you.